Hello everybody and welcome to lecture today. We're going to be talking about section 5.5, the fundamental theorem of calculus. So let's write that. Yeah, so let's box this. Alright, yeah, so the fundamental theorem of calculus, let's just jump right into it. It's a theorem, and what it's going to help us do is it's going to help us evaluate these things that we call definite integrals. And I think we've seen definite integrals, and maybe we haven't. I mean, the only reason you would have is because we understand them as finding the area under the curve. We call these definite integrals. Here, let's just review that. So we write, or when we write, the integral, that's the integral symbol, it's like an S, of f of x dx. This is an indefinite integral. And the biggest thing to note there is that there aren't any bounds on the integral itself. There's nothing written here and there's nothing written here. And in section 5.4, we were starting to write stuff there. So when we write the integral from a to b of f of x dx, this is a definite integral. And I guess how I think about these is with the definite integral, when we have the bounds like this, we can actually find it's tangible. We can find the area under the curve of this function. And just so we see a picture, and I think you guys have seen this before, but if we have 2 points A and B, and we have our function which looks something like this, and let's just call this f of x, then the definite integral will find this area exactly. And I guess the usefulness of this, I think, is it helps us actually find the area of sort of weird functions. I guess up to this point, we've only been able to, pretty much since elementary school, been able to find the area of like a triangle or a rectangle or a square, right? These are really basic shapes that I think everyone kind of knows how to find the area of. Now we have these tools that help us find the area of really weird shapes. I mean, this shape right here is a very strange shape, and I think if I were to ask you to find the area of it, you'd probably struggle. I mean, I would if I didn't have calculus. Okay, so that's the point, and that's why definite integrals can be somewhat useful. Okay, and what I'm going to do is we're going to actually explicitly find the area of this shape, pretty much no matter what f of x is, okay? And that's the goal. We want to find some type of algorithm that helps us with this. Okay, so let's do that now. So it's actually, what's going to help us do that is the fundamental theorem of calculus. So let's list it as a theorem. This is the fundamental theorem of calculus. And this is the big topic in calculus. This is what everybody, wants to get to. This is the point of calculus. So here we go. If f is a continuous function on the interval, the closed interval, AB. Let's actually be a little bit more intentional about this f. Let's make this a lowercase f, okay? It's going to matter. If f is a continuous function on AB, and capital F is any antiderivative, of little f, then, and here's the punchline, getting really low on the page, I probably shouldn't do this, but whatever, then the integral from a to b of little f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Now there's only a couple things that we need to unpack with this theorem. And the main things, I guess, that would sort of confuse me just initially looking at it is the fact that it says any antiderivative. Just think of this as the normal antiderivative. So, and we'll obviously go over an example of this. But the antiderivative that we take, I think up to this point it's clear that we need to add c every time, right? And that can get kind of annoying. But here's the reason it's nice is actually you don't need to add c anymore when applying the fundamental theorem of calculus. Some of you are probably really happy about that. And you'll see why we don't have to necessarily add c when taking definite integrals. We don't need to add c at all. And you'll see why. But that's why we say any antiderivative, because any c is going to work, so we don't even really need to add it. It doesn't affect the answer. So we'll see an example of that pretty soon here. So let's jump into it. So here's an example. Let's go ahead and use the fundamental theorem. Let's use the fundamental theorem to find the integral from 1 to 2 of 2x plus 3 e to the x minus 4 over x dx. And just as a side remark, I often think of this dx, just so people aren't super intimidated by this weird integral symbol and dx symbol. These are the two new symbols, not to this chapter, or not to this section, but definitely to the chapter. And think of this as kind of in some sense, kind of like this beginning parenthesis, right? It's telling us where we're going to start taking such an integral, and this dx is kind of telling us where we need to stop taking the integral. So just think of it as we're taking the integral of whatever's inside of these two things. Okay, you can somewhat ignore the symbols, because once you know what they mean, you can just sort of ignore them. And so now what we're going to do is we're going to focus our attention on this. We're going to focus our attention on the integrand. And I'm going to actually note, so let's just write the solution and how we're going to do this. I'm going to note one thing immediately. The first thing that I can note, which is something we learned in section 5.4, is, well, I'm trying to find the area under this curve. Whatever this curve looks like. I have no idea what the curve looks like. Even myself, I really have no idea. And so, but one thing I do know is I want to find the area under the curve between these 2 points. And I don't know, but it roughly, I have no idea what the function looks like again, right? I always kind of just draw this one, but we want to find this area right here. Boop, boop, boop. Right? We want to find that area. This is kind of what our function looks like. And how we're going to do that is we can split it up at each addition and subtraction mark. So we can just take these individually. So the integral that we actually care about is, well, first of 2x plus the integral from 1 to 2 of 3 e to the x plus, or dx, plus the integral from 1 to 2, I should really say minus, of 4 over x dx. And that's what we want to find. Another thing that I'm going to recognize is that I can actually pull out constants. So if I have a constant here, 2, a 3, a 4, I can pull those out. Rewrite it as 2 times the integral from 1 to 2 of x dx plus 3 times the integral from 1 to 2 of e to the x dx minus 4 times the integral from 1 to 2 of 1 over x dx. Now I'm just going to pause and see if you guys can make sure everybody can gather their thoughts there. All I'm doing is using this thing that I would call linearity of the integral. I can split it up at the addition symbols, and I can also pull out these constants. I can pull out these constants, which that 2 is here, I pulled it out. That 3 is here, but I pulled it out, and that 4 is here, I pulled it out. I kept that negative. Okay, and the reason I would do that is because I do know how to take the integral of this, right? I turned this kind of really difficult, long function into 3 really quite easy functions to take the integral of. So let's just go ahead and do that. We can use what I call the anti-power rule, or whatever you want to call it, and I notice that there's kind of the exponent on this x is just 1. So I add 1 to the power and divide by the power. And divide by the new power. That's what I say. I always say that. Add to the power and divide by the new power. So if I add 1 to 1 here, obviously you get 2, and you divide by the new power. So we get x squared over 2 is the antiderivative of x. Since they are definite integrals now, I don't want to just immediately move on. What I'm going to write is I'm going to write this vertical bar from 1 to 2. Okay? Notice the order. The order originally was 1 to 2. I also wrote that 1 to 2. This vertical bar means evaluated at. And this is used all across math. And we're just saying that we're evaluating this antiderivative from 1 to 2. And you'll see what I mean by evaluating. That's going to be using the fundamental theorem. But just write this for now. Try to just go through doing this. Now I'm moving on. The integral of e to the x is e to the x. That's the antiderivative, so I'm just going to write that. But notice I'm going to have to evaluate it from 1 to 2. And then, similarly, for the derivative of 1 over, or the antiderivative of 1 over x is going to be the natural log of the absolute value of x. Evaluate it again from 1 to 2. And if you ever forget about what the antiderivative of 1 over x is, I always just kind of like a hint, I guess. 1 over x is the same as x to the negative 1. And if you try to add 1 to that power, you'd get 0. And the point is that you always add 1 to the power and divide by the power. We can't divide by 0. That's just something you cannot do in math. So I always kind of run through that in my head. I actually did it this time because I had initially forgotten. If I add 1 to this power here, which is the same as this function, and divide by it, I get a divide by 0 error. Okay, I can't use the standard power rule, so it must be that the derivative of this is the only other thing, the natural log. Okay. So, notice nowhere in here did I add c, right? I never added c. That's kind of goes against everything that most calc professors believe in, but I mean, it's okay. Because it's not going to actually affect the answer at all. But let's go ahead and just apply the fundamental theorem of calculus and see what happens. So I'm going to, first, this is my antiderivative already. This is my antiderivative of this original function. All I need to do is input this top value in first. Oh, I guess I can cancel out these 2's right? I don't need those there. So it's just going to be 2 squared minus, and now I enter in the bottom value, minus 1 squared. And yeah, I could have a 2 over, I could have the 2 over 2 here and the 2 over 2 here, but 2 over 2 is just 1, so I should just cancel those immediately. And we'll just leave that as that. Right now we have actually evaluated that. So this is just going to be 4 minus 1. Don't write the actual solution yet. We want to finish this out, but this is just going to be 3. Okay. Now we just do this. We go 3e squared. Notice what I'm doing. I'm putting that 2 into here. And I'm going to be putting, and then I put minus 3e to the 1. And now minus, this is important, I'm going to put parentheses here, because now I do the same thing to this, but notice I have to subtract this entire thing. So I do minus 4 times the natural log of the absolute value of 2, minus 4 times the natural log of the absolute value of 1. End parenthesis. Okay. Now let's just evaluate this. This first piece, we already talked about it. This is going to go to 3. The second piece, there's nothing you can really do to simplify that. I mean, you can possibly factor out a 3. Let's do that. E squared minus e. And over here, well, the natural log of 1 is actually just 0. E raised to the 0 gives us 1. So this piece is just 0. So we just need to subtract off 4 ln with the absolute value of 2. And, well, that's it. We're done. That's the solution. And I suppose if I was on Pearson, you could just enter that as is. If you're in a situation where you need a decimal expansion, you can plug it into a calculator or a computer and get an actual number. But this right here, I promise, if you put it into your computer, you can do it right now. This is just going to be some number, and that number is going to be this area right here. It's very strange. It is decimal and it's scary and whatever, but it's the solution. This is what I'd be looking for. Now, why didn't I have to add c? I do want to remark why I didn't add c. Notice that if I would have added c here, if I would have added c right here, then that c would also be right here, right? If I would put 2 into here, and I had a plus c right here, that plus c would also exist here. And it would also exist right here. Notice I had a plus c, but then I'm subtracting off that plus c, right? So notice that even if I were to add that in, the fundamental theorem would just cancel out my plus c's. So there's nothing that I would need to do. Okay, so that's the fundamental theorem in a nutshell. This is the process I want everyone to kind of get used to doing. So an example that you should try, that's extremely related to the one we just did, is evaluate the integral from 1 to 3 of 4x minus 2e to the x plus 5 over x dx. And as you can tell, that's like extremely similar to the one we just did, but it's really good to try to walk through this on your own, okay? And you can check your work kind of along with my work. I don't really want to walk through this right now. How much time do we got? 20 minutes in? Yeah, so I'm not going to walk through this right now because I want to get to how to use the fundamental theorem with substitution, which is something that we learned in one of the previous sections. But this is something that you should try on your own. And if you want to know the solution, you can go look in the book and try to follow their steps. But it's really good to just try this on your own. Okay, so let's go ahead and go to the next example. Oops. Yeah, right now is when I would ask for questions, of course. feel free to email me your questions or try to pop into office hours next week or something like this. But yeah, I guess we'll just move on. So let's go ahead and try to evaluate the integral from 0 to 5 of x over x squared plus 10 dx. It's not obvious how to take the integral of this, and that's that's kind of the point of this next example, is that sometimes we have to use u substitution to find our integrals, but we also want them to be definite integrals, and we want to find the area under this curve in particular, okay, between these 2 points. So the first step that we're going to do is, first step is find the antiderivative. So first find the antiderivative, meaning find the integral of x over x squared plus 10 dx, but without the bounds, right? We just don't have the bounds on the integral, and this is just finding the antiderivative. We don't care about the area under the curve or of anything like this. And so how we're going to do this is we're going to have to do this by using u substitution. And I suppose I know that immediately because I've seen a lot of these types of problems, and I kind of know what the solution is going to be. So it's easy for me to recognize what I'm going to have to do. I guess the more you see, the more you know. And in this case, I just kind of know that I'm going to have to, I can't take the integral of this as it is. It's like I can't add 1 to the power of anything because there's just too much going on. And when there's just too much going on, it's probably going to be a u sub problem. So I'm going to let u equal x squared plus 10. And let's see if we can make this look any simpler. We will be able to. So I'm going to make the denominator just u. And if I take the derivative of both sides, which is what you do when you do this u substitution process, you end up getting du dx is equal to 2x. The one thing that I always recommend whenever I'm doing problems like this is I just immediately solve for this dx here by multiplying it up here, and then taking whatever this coefficient is and dividing it out. So you end up getting dx is equal to du over 2x. I always section it off because those 3 things, these 3 lines that I wrote, right here, here, and here, I'm going to use to make this problem look a little bit easier. So I always tell myself, I always say, this is for a future hunter, the goal is to make this look easier, and I can now, because instead of writing this as my denominator, I can write it as u. I told myself I can do that. Now x, this numerator that I just wrote, it's not explicitly equal to anything over here, right? X, okay, I kind of see an x here, but it's not explicitly equal to anything, so I'm just going to write that. And the denominator is just u. dx, though, on the other hand, it is explicitly something. It is du over 2x. So that's already a lot cleaner, and we can even make this even cleaner. This x and this x can cancel each other out. So I can instead write this as the integral of 1 over, well, there's a 2 down there, so 2u du. Okay, and that 2 came along because it was in the denominator here, so when I substitute that in, it's still down there. Okay, and I don't really like having that 2 inside of my integral. I'm going to pull out, since that 2 is in the denominator, that's the same as 1/2 times 1 over u du. So the integral of 1 over u du, kind of by the same logic as I was describing before, is the natural log of the absolute value of u plus c. But I gave you this problem in terms of x, right? I mean, the original problem here is given in terms of x. Right now our solution is in terms of u, but let's change it back to x's because that's what I think is useful. So we're just going to write the absolute value 1/2 times the natural log of the absolute value of x squared plus 10 plus c. And just so we know, instead of writing u, I know that u is actually equal to this, so I'm going to substitute it back in. It's important to remember the order in which I'm doing this. I didn't substitute it back in before I took the integral, right? I made the integral look easier, took the integral, and then substituted it back in. Okay. And I had to add c here, and you'll see that c won't matter at all. But let's go ahead and go to the next page, and I hope everybody kind of has this written down now. Because we're going to be using that. We're going to be using the fact that the antiderivative of this is this. Okay. So step 2 is use the fundamental theorem of calculus. And how we're going to use that is we're going to remark, well, what was the original problem? We wanted to find the integral from 0 to 5 of x over x squared plus 10 dx. And the fundamental theorem tells us that all we need to do is find the antiderivative of this and evaluate it at 5, evaluate it at 0, and subtract them. How I was writing that before, and how I want you to get used to writing this, is using that vertical bar, okay? So remember the antiderivative. We just found the antiderivative of this. The antiderivative is the natural log of the absolute value of x squared plus 10 plus c. And the fundamental theorem tells us that we just need to evaluate it from 0 to 5. Don't get intimidated by that vertical bar. I mean, all it's saying is, remember, this is notation for evaluate this at 5, evaluate this at 0, and subtract them. So we take the natural log of the absolute value of 5 squared plus 10. Oh, wait, I forgot my 1/2. Forgot my 1/2. Maybe some of you caught that. Very important that we have that 1/2 in there. Okay. So I evaluated that at 5, and then I'm going to evaluate it at 0. You know what? Just to really emphasize this, I know it's like, oh, well, you might not have to erase that. The only reason I'm going to erase it is because I'm going to put in that plus c. So 5 squared plus 10 plus c minus the quantity 1/2 ln of 0 squared plus 10 plus c. Okay? And this is why we don't really care what that c value is, because here I added c, and then I'm going to be subtracting c off again, right? So it's like, this c, it doesn't really matter that I wrote it. But it's important to recognize why we don't need to write it, I guess. So anyways, let's just start kind of simplifying this. This first piece, well, we don't need to take the absolute value anymore, because 35 is already positive. The 35 came from 25 plus 10, so I just simplified it to be 35. I don't need to write the plus c anymore because this c canceled with it. The natural log of 0 squared plus 10, that's just the natural log of 10. So minus 1/2 times the natural log of 10. And that's the solution right there. There's other ways we can actually simplify this to make it look a little nicer. And maybe it's not a bad idea to do that, but this is something you could plug into Pearson, it would work. And I just want to make sure that everybody's clear on what the two steps were. First, we found the antiderivative. Then second, we evaluated the antiderivative at the two endpoints. and subtracted them. The order in which you subtract them is very important. We first evaluate at 5, which is the top, then we subtract off the antiderivative evaluated at 0, and that's the reason I like to write it in this order. Just read it from top to bottom. Just like you read a page, right? Like we read a page from top to bottom, right? Sometimes that helps. So that's the fundamental theorem of calculus. I mean, that's all of it. We, as an alternate exercise, which is something that I think you should, work out in your own free time. Maybe right now, this is a related problem. Let's see. You can do the evaluate. The integral from 0 to 1 of 1 over 2x plus 4 dx. That's a good problem. Just see what you get. You're going to have to use U substitution here. I mean, that's a spoiler alert. As a hint, notice that I don't really like that there's a really big expression in the denominator, so maybe that might be a good choice for you. So go ahead and try that as a problem, but other than this, that's all I got for you. So I hope you enjoyed the video, and I hope the rest of your semester goes smoothly. I did post a homework for section 5.5 on Pearson. It's really just all of these. It's just practicing using the fundamental theorem, and it's also practicing using the fundamental theorem with U substitution like we did here in this last example. All right, thank you for listening.